All right, let's dive right in. We're going to take a journey to the very center of, well, everything. We're talking about breaking down reality itself into its absolute smallest parts to figure out what really holds our universe together.
I mean, think about it for a second. What are you, the desk you're sitting at? Even the stars in the sky. What are they all really made of? It's a huge question, right? But the answer is almost, well, unbelievably tiny. So let's shrink ourselves down, way past what we can see, past molecules, even past the atoms themselves, to find the fundamental little particles that make everything tick.
Okay, so we've all heard that everything is made of atoms, but what makes a gold atom gold and an oxygen atom oxygen? The secret is in even smaller pieces, these things called subatomic particles. They're the real MVPs. These tiny little guys are the reason gold is heavy and shiny, and oxygen is the gas we breathe. They literally define an element's entire identity. So if we dive into the very center of an atom, into its dense core called the nucleus, that's where we find it. The one particle that's in charge, the one that defines exactly what element we're looking at. Let's go meet it. And here it is, the proton. I mean, even the name sounds important, doesn't it? Well, it absolutely is. The number of protons an atom has is its ID card, its fingerprint. It is the one single non-negotiable rule in the atomic world that can't be broken. So here's the rundown on our proton. It's got a positive charge, a mass we call 1 atomic mass unit, and it lives in the nucleus. But honestly, the most crucial thing, the only thing you really need to remember, is its role. It's all about the count. If an atom has 6 protons, it's carbon, period. If it has 7, it's nitrogen. No exceptions. That number is so important, we call it the element's atomic number. Yeah, this is the perfect way to think about it. Protons really are like a person's national ID. That number defines who you are, and you can't just change it. It's the same for an element. You simply cannot change the proton count without changing the element into something completely different. So, the proton might be the star player that defines the team, but it doesn't work alone. There are 2 other particles in the mix that determine an atom's weight and, maybe more importantly, how it actually interacts with the world around it. Let's meet the rest of the team, the supporting cast. First up, we've got the proton's roommate inside the nucleus, the neutron. And yeah, just like the name suggests, this particle likes to stay neutral. The neutron, you see, has no electrical charge at all. It's totally neutral. But it's got basically the same mass as a proton, that 1 atomic mass unit we talked about. Its main job? Well, it adds weight, sure, but its real job, its most important role, is to keep the nucleus from literally flying apart. And this glue idea is so important. Just think about it for a second. The nucleus is jam-packed with all these positively charged protons. And what do positive charges do when they're close together? They repel. They push each other away. So the neutrons act like a buffer, a kind of nuclear peacekeeper, holding everything together against those powerful repulsive forces. And that brings us to our final particle. This one doesn't live in that crowded nucleus. Nope, it hangs out in the vast, mostly empty space around the nucleus. Let's meet the electron. Okay, so electrons are these tiny, tiny particles with a negative charge and, get this, almost 0 mass. They're incredibly lightweight. But you should absolutely not let their size fool you. Electrons are the action heroes of the atomic world. Because they're on the outside of the atom, they're the ones doing all the work, interacting with other atoms, forming chemical bonds, and even creating the flow of electricity that's powering your device right now. You know, the classic way to picture this is to think of electrons as planets orbiting the sun. It gives you a great mental model. The heavy protons and neutrons are like the sun at the center, and these zippy little electrons are whizzing around in their own specific energy levels, or shells, just waiting to interact with the universe. All right, quick recap. We know the proton number is locked in. 6 protons always means you're looking at a carbon atom. But does that mean every single carbon atom in the entire universe is a perfect clone of every other one? And this is where things get really cool. If that core identity, the proton count, is locked, where can an atom get a little bit of variety? Where's the wiggle room? Well, the answer lies with our neutral friend we met a minute ago, the neutron. And this brings us to a super important word, isotope. Basically, an isotope is just a different version of the same element. Think of it like a family. Every member of the carbon family must have 6 protons. That's the family rule. But they can have different numbers of neutrons. They're all still carbon, just slightly different versions. Just look at this table. It's a perfect example. We've got 3 types of carbon. Notice the proton column? It's always 6. That's what makes them all carbon. But now look at the neutrons. Carbon-12 has 6 neutrons. Carbon-13 has 7. And the heavy one, carbon-14, has 8. They're all carbon, they just have different weights, or what we call different mass numbers. So who cares, right? Why does this even matter? Well, that extra weight from those extra neutrons can sometimes make an isotope unstable. And that's exactly what happens with carbon-14. It starts to break down or decay at a very predictable rate. This is amazing for archaeologists because they can measure how much carbon-14 is left in something ancient, like a bone or a piece of wood, and figure out exactly how old it is. It is literally a time machine. Okay, we are almost at the finish line. We've established that protons and neutrons each have a mass of pretty much 1. So why is it that when you look at a periodic table, the atomic mass for an element is almost never a nice, neat, whole number?
Yeah, let's stick with carbon. If you look it up, its atomic mass is listed as 12.01. Not 12, not 13, 12.01. How is that even possible if its building blocks have these nice whole number masses?
Well, here is the secret. That number you see on the periodic table, it isn't the mass of one single atom. It's actually a weighted average of all the different isotopes of that element that exist out in nature, based on how common each one is. It makes perfect sense when you see it like this. If you were to grab a random scoop of carbon from anywhere in the world, almost 99% of it would be that lighter carbon-12 isotope. The heavier versions, like carbon-13, are way, way rare. So because there's so much more of the 12 version, the average mass gets pulled way down close to 12, just leaving us with that little bit extra, giving us that final number of 12.01.
So there you have it. We've met the whole atomic cast. The proton, which gives an atom its fundamental identity, the neutron, which adds mass and keeps everything stable, and the electron, the little live wire that creates all the action. So, which one truly runs the show? I think the real takeaway is that it's not about which one is most important. It's about how these 3 incredibly simple particles, working together in perfect harmony, can build our entire, complex, amazing universe.